Hi, this is a video that's going to demonstrate the calculation of the area moment of inertia of a built-up cross-section. And by built-up cross-section, we mean two or more components that are attached, welded, bolted together, whatever, so that they behave as one, typically in a flexural stress application. Okay, I'm going to pull data from this handout, this the metric structural steel handout. Specifically, I'm going to bring together a C channel and a wide flange beam. So I'm randomly going to pick some, or semi-randomly. I'm going to pick a C channel as the base. I'm going to use a C 150 by 19. So this row right here, C 150 by 19. Okay, I'm just going to sketch it. Okay, here's the proposal. Okay, a C 150 by 19 like this. Okay, and on top of that, a W 200 by 22, which is further into the table. These dimensions of this W-shaped stuff, it's all the same all over the planet, really. These are metric dimensions, but officially it's actually an inch-based product. If you found the U.S. customary dimensions for these materials, it'd be the same dimensions, just in inches. So I'm going to put a W 200 by 22 on top of that. And now you should know what these dimensions mean. A W 200 by 22 means it's 200 millimeters nominal height or depth in the world of beam speak, and 22 kilograms per meter. Okay. And similarly, a C 150 by 19 is 150 millimeter nominal depth and 19 kilograms per meter. So here's the proposal. Okay, W 200 by 22 and a C 150 by 19 structural steel. Okay, and we'd weld that or something. You know, you'd obviously have to weld it in here. That's a matter for a different analysis. You know, how much weld, how strong does the weld have to be? Actually, to do that analysis, you'd have to have the area moment of inertia. So what we're doing here is fundamental to design in a beam cross section like this. Okay, all right. The problem is that the moment of inertia of a W 200 by 22 is known. You look it up in the table, and the moment of inertia of a C 150 by 19 it's known. It's axis y values. You just look it up in the table. But together they contribute differently to the overall moment of inertia of the beam, and so there's a calculation to be done, and it's fairly complex. Okay. Now this is a composite shape. This is two pieces of structural steel. It could also be, you know, a rectangle and a piece of flat bar or something. It doesn't really matter what the shapes are. The idea is that the individual shapes, in this case a wide flange beam and a C channel, you can look up the data or otherwise quickly determine the data for those individual shapes. And the problem is, how do they behave as a whole? So that's what we're doing here. Okay. Now there's two things to do. We first need to find a centroid. The location of the horizontal centroidal axis. The vertical axis is obvious. It's right in the middle of the thing. It's right down the middle. It's by inspection. It's all symmetrical. It's where in this lateral plane, where does the centroidal axis located? And then once we have that, we can calculate the area moment of inertia. Now, area moment of inertia is such a common thing that we typically just call it moment of inertia, which is capital I. Okay. So the first thing is the centroidal axis. Now, somewhere in here, and probably somewhere around there, give or take, is the location of the centroid, which is the balance point. Another way to think of the centroid is it's equal amount of area above it as there is below it. That's just as simple as it gets. It's a balance point. So this amount of area here would equal this amount of area here. It's just like being on a teeter-totter, you know. You get two people equal body weight on a teeter-totter, put them on each end, and the centroid of the assembly would be the fulcrum of the teeter-totter. It's a balance point. Okay. But we have to know exactly where it is. We can't just approximate it. We need to have an exact number because it's going to carry forward into other calculations. Okay. So you've seen the centroid calc. I've got a formula sheet here. The centroid calcs are right here, right? It's we don't need the x bar. That's right smack in the middle. That's the distance from the laterally to the right. But we need y bar, okay? And as you've probably seen, it's beneficial to call the datum. We need a datum point. Let's call the bottom surface the datum, okay? And then y bar will be right here. Now you can make any surface a datum. You can make the top of the assembly, the top of the shape the datum, and so on, and you won't get a wrong answer. The location of the centroid is not debatable. But if you make the top surface the datum, then you're dealing with a bunch of negative values, negative y values. Or you can make the top of the C channel the datum. You can make this backbone of the C channel the datum, and then you're going to have negative values. You're going to have negative values for the C channel value. Just pick the bottom surface as the datum, and then everything is positive. You got no issue trying to remember negative, positive, whatever. Everything's positive. Okay, so we're going to do that. Step 1. Here's a calculation. Y bar equals the sum of the individual areas times their individual y bars over the sum of the areas, okay? And don't get all worried about the I value. That just means it's a placeholder for how many areas you have. We have 2 areas, so this would be area 1 y bar 1 plus area 2 y bar 2. And the denominator will be area 1 plus area 2. So it's just math speak, okay? I'm going to use subscript C for the C channel and W for wide flange. So it's going to expand like this. Area C channel, Y bar C channel, plus area wide flange shape, Y bar wide flange shape, over the area C channel plus area wide flange. That's how that converts, okay? Now you're thinking, all right, now this is where it gets difficult. Well, perhaps, but I don't think so. This data right here, we have to be careful for sure. We're going to have to read the tables of the structural steel appendix, but it's not. It's just numbers and care. Okay. All right, here we go. Area C. Now, some people make a table up. It's not a bad way to go. A big matrix, you know, with these values. I've got 1, 2, 3, 4 distinct values, and they're can be challenging. So some people make a table with the values, and then at the end of it, then they process those values into this equation. I don't think I'm going to do that. I think I'm going to just do the area C, y bar C directly. So here we go. Area C. So y bar equals, well, area C is the area of the C channel. It's just that simple. So you just look it up in the table. You find the value. That's wide flange. So C channel. C150 by 19. It is, so it's a double-sided table. I have it double-sided or double page. So C150 by 19. The first parts, we'll need that info later, but flip it over. And on the 19 row, the rows are so the 19 right here is the data. And you see up on top, there's a cross-section. It's off the screen there. Here's the cross-section, right? And anyways, area is right there. Surface area. No, that's surface area. Maybe it's on the previous page. My bad. Yeah, it's on the previous page. My bad. C150 by 19. Area. Okay, there we are right there. 2450 square millimeters. So that's area of the C channel, cross-sectional area of the C channel. 2450 millimeters squared. Okay. Now, that's not difficult, but Y bar C. Well, Y bar C, I'm going to change a different color here. Y bar C is this distance, the C channel by itself. It's got its own balance point, and it's in the table, and it's somewhere, it's not in the middle of the back rib. That wouldn't be the balance point. Remember, it's the equal area on both sides of the axis. It's actually in here somewhere, like that. Okay, and Y bar C, the one we need. Now the table doesn't give us this value directly. We have to search for it, but we need this value right here. Y bar C. But if you go to the table, There's a few things that are playing around here. Use a straight edge in a table whenever possible so you don't misread it, okay? Up here, right in here, that's fine. There's a centroid right there. That's what that line is, YY, okay? Now, first of all, our C channel is oriented 90 degrees. So the axis we're interested in is this vertical YY axis. You know, our orientation is like that, right? That vertical axis is located by dimension x off the back side, but that's not the dimension we need. We need the dimension from this side to there, which we don't directly have. So we have to work for it, okay? So the dimension x is 12.9 millimeters. Given right there, 12.9 millimeters is x. But I need to know the entire dimension b here, because the y bar c that I need on my print here is b minus x. That's what I mean by you got to kind of, hunt through the table. So I need dimension b, which is right here. I'm on the 19 row. B is 54, okay? So the total height is 54 minus the x dimension, which is 12.9. So 54 minus 12.9. Y bar C is 54 millimeters minus 12.9 millimeters. Okay? Whatever that is, it's 41 something or other. Okay? Double check your numbers, make sure you didn't do some mistake there. Okay? That's Y bar C. Area wide flange. Well, so now the same thing happens for the wide flange, and it's got its own flavor of challenge, if you will. Wide flange, W200 by 22. Okay. The area is easy enough, right? 200 by 22 right here. Area is, I'm off the chart there, it's total area. 2860. 2860 square millimeters, so that's area W, 2860 millimeters squared, times y bar W. Well, y bar W, now in other words, where is the centroid of the W flange reference to our datum? That's what that y bar W is. It's right here. Here's the centroid. It's right smack in the middle. It's a nice symmetrical component, unlike the C channel. So y bar W is right here. And we have to fight for it because I don't have it directly in the table. Now I've already got a bit of work done because clearly it's going to be half the height of the W flange. See that? It's going to be from there to there, plus the flange thickness on the C channel. Well, I have that number. That's 54. This dimension right here is 54. So it's 54 plus half the depth of a W200 beam. Okay. Now watch out, these W shapes, sure, W200 is nominally the height 200 from here to here, but just be sure about that. I'm going to flip the page over, W200 by 22, and see that? It's actually 206. See that? On this page, the 200 is a nominal value, meaning it's, give or take, and the actual value is 206. Well, the centroidal axis is halfway up. This D dimension is 206. The centroid is half that way up, 103. But y bar W is 103 plus this length here. So it's 54 plus 103 millimeters. Okay. Now you might have to double check that or whatever. You might have to go back and just confirm, pause the video and confirm you can get that, okay? The denominator is easy because you already have the areas. You just add them together. 2450 square millimeters plus area wide flange 2860 square millimeters. And now you got to do the calc, which is a matter unto itself. So here's the calculator. Okay. And so you just crank it out. Do it twice, hey? I like to start in the middle of parenthesis. Anyways, it doesn't really matter how you do it. If you have a graphing calculator, you can just put it all in and confirm it's correctly entered and then hit enter. But I don't have such a calculator. So 54 minus 12.9. Whoops. My first go around I got 103.5, and you know what? That's pretty darn reasonable. 100, in other words, it makes sense. It's not like it's definitely. So that'd be, you know, but where I drew that thing, that's Y bar. One more time, you gotta double check these numbers, and I'm not working off of a solution here. I'm doing this in real time, so I've got to, you know, I don't know if that's the right number basically. If I get the same number twice, it's almost certainly in my books the right answer. Okay. All right. Third time's a charm. Bit more care of that. All right, 103.52. Okay, that's Y bar. Okay, that's the centroid. That's a means unto itself. Now, the area moment of inertia calc is kind of the same, but kind of not. It's got its own. You know, you might have seen this equation, right? The parallel axis theorem. That's not very helpful by itself. Okay, but I will say this about the parallel axis theorem: the I is the value from the table. The moment of inertia of the cross section, whether it's structural steel or rectangular, whatever, by its lonesome. A is the same area, so we can pick that up from the previous centroid calculation. And D is the distance between the centroid of the individual component to the centroid of the whole cross section, and you square it. Okay, the devil's in the details. Let's go have a look at this. So it looks like this. Here's the whole thing. IX, I'll call it. Often, you know, XX like that, which is the moment of inertia about the centroidal axis right here. Let's call that XX. Okay, the moment of inertia, the area moment of inertia about that centroidal axis, IX, is I C channel plus area C channel distance squared, right? So that's the C channel's contribution, plus I wide flange plus area wide flange times distance squared. And I guess I got to put a little subscript on there because they're not the same distance. And that's the wide flange's contribution, all right? All right, slide this up a little bit. Here we go. Again, some people make a table. I don't really bother with that. But the moment of inertia of the C channel, well, you just look it up. But wait, it's not that simple, because when you look up the C channel in the table, it's positioned what I call the good way. It stood on its edge, which has a very large moment of inertia. Well, we don't have that orientation. Ours is like that. Okay, so it's, as far as the table is concerned, it's the moment of inertia about this YY axis. So that's a important detail. So I need the moment of inertia of the C channel in this orientation. So it's on the table. Throw a straight edge on there at 150 by 19, but it's not IX. That would be the, if it was vertically oriented, it's because it's horizontally oriented, we need IY, which is 0.425. Now watch out. All these numbers are times 10 to the 6. These are 0.425 million millimeters to the fourth. So watch, there's a header there, okay? So IY or IC, you know, this one right here, the moment of inertia of the C channel is 0.425 times 10 to the 6 millimeters to the fourth. Make sure you know how to get that. That's IC, okay? Plus the area of the C channel, well, that's right up here. We already have that, 2450. Just grab it from the centroidal axis calc. Times the distance. Now this is one more little, you know, there's lots of speed bumps here, okay? One more little check here. The distance, the distance for C channel, is the distance between the centroid of the C channel by itself and the centroidal axis of the whole section. Well, the distance from the center of the C channel, from our datum, if you will, is this number right here. 54 minus 12.9 is 41.1, right? I never figured that out, but it's this distance from here to here. okay, from the datum. And of course, the distance to the y bar, or to the centroidal axis from the datum, is our y bar, 103.52. So the distance here is the gap between this centroidal axis for the C-channel alone and the centroidal axis for the whole composite shape, and that distance is, okay, I'll open a bracket here. That one should have been a square bracket. So it's 54 minus 12.9. I'll do that number right there. 54 minus 12.9. 41.1. This is 41.1 millimeters. Okay. That's this distance right here, YC. Okay. So the distance here is 103.5. It's the remainder. 103.52 minus 41.1. 103.52 millimeters minus 41.1 millimeters, and that's the DC. And square that thing. Okay. Close bracket. Plus, that's the contribution of the C-channel to the moment of inertia. Now the wide flange. Open bracket. Plus sign. I wide flange. Well, the moment of inertia of the wide flange. Now the wide flange is positioned, the good way, if you will. It's stood up, like that, right? So I need the IX value for a W 200 by 22. So you look it up. W 200 by 22. IX. 20 times 10 to the 6. Do not forget the 10 to the 6. You'd only be out by a factor of a million. 20 million. All right? The I value of the wide flange by its lonesome is 20 times 10 to the 6 millimeters to the fourth, plus the area of the wide flange. Well, that's right up there. 2860 millimeters squared. Times, now the wide flange. Now you get the idea here, right? YW. We need this gap right here. That's distance wide flange. In fact, I'll put it on there. Here's distance C. This one here we used here. Here it is here. Distance C is right here. Distance C is right there. Distance C. Okay. And distance wide flange, the parallel axis. That's why I call it parallel axis, because the centroidal axes are parallel. That's this distance right here. Distance W. Well, that's YW minus, right, minus Y bar. YW is this thing. 54 plus 103. That's 157 millimeters. So that gap, better known as DW, is 157 minus 103.52. So it's very, and then square that, close bracket. So it's a very, it's unforgiving. If you make one mistake, yeah, it's completely done. But that's a lot of engineering's like that. Let's do this calculation here. It's a bit of a beast, hey? In fact, I'm going to calculate these things individually. I don't normally do that, but in the interest of getting the right answer, that's a 10, by the way, I'm going to calculate these first, right? In other words, I'm going to calculate the contribution of the C channel, this one, and then the contribution of the W shape. So I'm going to start in there, 103.52, right? Minus 41.1, and then square it, okay, times 2450 equals, so that's the adder. Look at the adder. The adder is, the AD squared number is way bigger than the moment of inertia of this I or a C channel by itself. Right? So that's the adder plus that, plus 0.425 exponent 6 equals 9. What is that? 9.971 times 10 to the 6 millimeters to the fourth. That's the C channel's contribution, plus then the wide flange contribution. 157 minus 103.52 is the distance, squared that, times the area, plus, and it's of the same order of magnitude as that. It's not nearly as big a difference as that, but it certainly adds a lot to it. Plus 20 million. Plus 20 exponent 6 equals, put that into 28.180 millimeters to the fourth. One more time, I got to check it because this is, again, I'm not working off of a solution here. So just doing all the calcs twice. Yes, 9.971 times 10 to the 6 millimeters to the fourth, and then the wide flange contribution 157 minus 103.52 equals square that times the area of the wide flange plus the wide flange moment of inertia if it were just by its lonesome. 28.1, that's a good number. The moment of inertia then, drum roll, the moment of inertia of the whole section is these two numbers added together. And I'm going to do that one again. I screwed that up. Do that again. 9.971 exponent 6 plus 28.18 exponent 6 equals 38.151 times 10 to the 6 millimeters to the fourth. It's an abstract number for sure. One more time, check that. Yeah, 38.151 times 10 to the 6. It's much greater than the wide flange by itself. It's double. See that? The wide flange by itself is 20 million millimeters to the fourth as a moment of inertia. You've almost doubled it by adding a piece of C-channel and beefing up the whole cross section. It's really about, in fact, moment of inertia like this is the further here's the mathematical rationale for doing these things. The further you can stretch the mass of the beam, the mass of the cross section away from the centroidal axis, the greater the moment of inertia. That's why wide flange beams look like the way they do, because it gets the flanges, i.e. the majority of the mass is away from the centroidal axis of the wide flange, and then you get this parallel axis adder, this d squared term really ramps up the moment of inertia. So here we see it also. It's really paying off. This is not a very stiff piece of steel by itself, a C150 by 19, especially flanges down like that. It's not particularly stiff, but when you weld a wide flange on top of it, you get a pretty big payout there. So, okay, so that's area moment of inertia. There's plenty of other questions around with two pieces of structural steel married together like this. They'd have to be welded or something to make them behave as one, but that's the approach. Be careful and use a straight edge on your tables and double check your work and so on, and practice makes perfect, or practice helps. Okay, all right, take care.